This is section 14.5, de Moivre's theorem. We are going to take roots and exponents of numbers, complex numbers in polar form. How do we use de Moivre's theorem? It probably would help you to know what it is. So, remember that yesterday we learned that the product of two complex numbers in polar form, WZ, is AB times the quantity cosine of alpha plus beta plus I sine the quantity of alpha plus beta. In other words, when you're multiplying two complex numbers in polar forms, you're first going to multiply their R values. This is the A times B, and then you are going to add the angles together and put those in for cosine and the sine angles. Now, let's say we wanted to square one complex number. We can use the product formula on itself. So, if Z is our complex number, R cosine theta plus I sine theta, and if we apply the product rule, we get Z times Z is R times R, since both magnitudes are R, times the cosine of theta plus I sine theta, cosine theta, I sine theta. Now, when you do this using the rule above, you get R squared times the quantity cosine of theta plus theta, because you're adding the angles together, plus I sine theta plus theta, because you're still adding the angles together. And if you simplify that, you see that Z squared is equal to R squared times the cosine of 2 theta plus I sine of 2 theta. Well, let's take this another step further. Let's now multiply that by another Z. So now we have Z times Z squared is R times R squared for the amplitudes, and then cosine of theta plus 2 theta plus I sine theta plus 2 theta, which means Z cubed equals R cubed times the quantity cosine 3 theta plus I sine 3 theta. So you start to see there's going to be a pattern, and this pattern is the foundation for de Moivre's theorem. If Z is a complex number in polar form, R times the quantity cosine theta plus I sine theta, and n is a positive integer, then Z to the n equals R to the n times the cosine of n theta plus I sine n theta. So for example, let's say we wanted to take Z to the 10th power, so our n value would be 10. So Z to the 10th would equal R to the 10th times the cosine of 10 theta plus I sine 10 theta. So this formula is pretty easy to apply, but sometimes just getting able to use it takes a little bit of work, and we'll see that in our first few examples. Example 1a, find radical 2 minus I radical 2 to the 5th power in x plus yi form. So this is going to require several steps, and I'll just repeat them now. I'll go through them and then I'll repeat them again. So the first thing you're going to have to do is convert this into polar form, which means R times the quantity cosine theta plus I sine theta. Then you're going to have to apply de Moivre's theorem by taking that number to the 5th power, and then you have to convert it back into x plus yi form. So let's see how this looks. Let's call Z radical 2 minus I radical 2. In other words, Z is the quantity that we want to take to the 5th power. So first we have to convert Z to polar form. So the absolute value of Z equals the square root of x squared plus y squared. Here our x value is radical 2, and our y value is negative radical 2, because that's the coefficient of I. So radical 2 squared, or x squared, is 2. Negative radical 2, or y squared, is also 2. So the absolute value of Z is 2, which also is known as R. So that means Z is equal to this. Now what I've done here is take this quantity and I factor out the absolute value of Z. In other words, the R value. I want to factor out R. So that leaves me with the 2 outside, radical 2 over 2 minus radical 2 over 2i inside. Now notice, if you multiply the 2 back in, you're back to what you started with inside the parentheses. So again, you first find the R value, or the absolute value of Z, you factor it out from the two numbers inside, and you're going to basically now use this to find out theta. Alright, so we know that cosine of theta is radical 2 over 2, and sine theta is negative radical 2 over 2. Why? Because we know cosine theta is x over r. So r is 2, x is radical 2. Or you can use sine theta. R is 2, and y is negative radical 2. So by looking at this, you can figure out which quadrant your theta is in. And based on the fact that cosine is positive and sine is negative, you're going to have a 4th quadrant angle. And since the reference angle for radical 2 over 2 cosine theta is 45, your theta value is going to be 315 degrees. Which means this number, the inside in polar form, is 2 times cosine 315 plus I sine 315. So that's a lot of work just to get it into polar form. Remember, first you got to figure out what the r value is, or the absolute value of z, factor that value out of the number inside the parentheses so that all your coefficients are between 0 and 1. Then you're going to use cosine theta and sine theta to figure out the reference angle, identify which quadrant your theta is in, and then come up with the value of the angle. Now we have to use de Moivre's theorem to find z to the fifth. So we're going to take z to the fifth equals r to the fifth, which is in this case 2 to the fifth, times the quantity cosine 5 times 315 plus I sine 5 times 315. So that's 32, because 2 to the fifth is 32, cosine 1575 plus I sine 1575. Well, we don't like to see our degrees that big, so we're going to basically find the angle coterminal with 1575 that's between 0 and 360. So if you subtract the 4 times 360, you're down to 32 cosine 135 plus I sine 135. Now, what you have to do to convert this into x plus yi form is figure out what cosine of 135 is and put that back in. So that's negative radical 2 over 2. Sine 135 is positive radical 2 over 2. That's multiplied by I. And now you redistribute this 2 to the fifth, 32, to get your answer. So if you distribute the 32, you get negative 16 radical 2 plus 16I radical 2. And that's what radical 2 minus I radical 2 quantity to the fifth power equals. So let's recap the steps here to solve this example. First, you take this value in here, you find the value of r by taking the square root of x squared plus y squared. You then factor out r so that you have fractional values for both the inside. Then you're going to use cosine and sine to figure out the angle. You'll have to figure out which quadrant the angle is in, get the reference angle, and calculate the appropriate angle for that quadrant for that particular reference angle. Then that gives you the number in polar form. Then you use de Moivre's theorem to take whatever this is to what power. So we want a z to the fifth. You take your r to the fifth. You multiply each angle by 5. Then you take your angle here. You find the angle coterminal with that angle between 0 and 360. And then to get it back into x plus yi form, you take the cosine and the sine of that angle, redistribute the r outside, and multiply it together. 1b, find negative 1 minus I to the sixth in x plus yi form. Give this one a shot. Alright, so first thing we need to do is convert it to polar form. So let's call z equals negative 1 minus I. So first we need to find the value of r, or the absolute value of z. So you're going to take the square root of x squared plus y squared, which in this case is 1 and 1. So z is radical 2. So what I said was you want to factor out this z value. So let's factor out a radical 2, which leaves you negative 1 over radical 2 minus 1 over radical 2i. But you want to get the radical out of the denominator. So if you multiply the top and bottom of each fraction by radical 2, this now becomes radical 2 times negative 2 radical 2 over 2 minus radical 2 over 2i. So now what we want to do is say that the cosine of theta is negative radical 2 over 2 and the sine of theta is negative radical 2 over 2. So since both cosine and sine are negative, we're going to have a third quadrant angle. And since theta, the reference angle, is going to be 45, our theta value is 225 degrees. So negative 1 minus I in polar form is radical 2 times cosine 225 plus I sine 225. Now you are ready to apply de Moivre's theorem. So you're going to take both to the sixth power. So z to the sixth is radical 2 to the sixth times cosine 6 times 225 plus I sine 6 times 225. Radical 2 to the sixth is the same as 2 cubed, or 8, cosine 1350 plus I sine 1350. You want to find the coterminal angle with 1350 that's between 0 and 360. If you subtract 1080, you get that that angle is 270 degrees. So your number is 8 cosine 270 plus I sine 270. Now that you have this, you're going to try to put it back into x plus yi form. So you calculate cosine of 270 and sine of 270. Cosine of 270 is 0. Sine of 270 is negative 1. So left inside you have 0 minus I. And if you redistribute the 8, the answer is negative 8i. So if you take negative 1 minus I to the sixth power, you will amazingly enough get negative 8i. Example 1c. go ahead and attempt this problem yourself and then check to see how you did. Alright, so let's call z 1 plus I radical 3. We're going to first convert it to polar form. So first you have to find r, or the absolute value of z. In this case, it's 1 squared plus radical 3 squared on the inside the radical. So radical 4, which is 2. So z is 4. Factor out a 2 from the 1 plus I root 3. And so left inside, you have 1/2 plus radical 3 over 2i. Now you need to find the value of theta. So the cosine of theta is 1/2, and the sine of theta is radical 3 over 2. Remember, sine of theta is the y coefficient here. Cosine theta is the x value here. Well, since both sine and cosine are positive, you're going to have a first quadrant theta. So the inverse cosine of 1/2 is merely 60 degrees. So 1 plus I root 3 in polar form is 2 times cosine 60 plus I sine 60. And again, this makes sense. Since both x and y are positive, you should have an angle in the first quadrant. So don't forget to check that. If you're not sure, look at the coordinate plane. Make sure the signs match the x and the y. Now we apply de Moivre's theorem and take z to the 4th power. So z to the 4th equals 2 to the 4th times cosine 4 times 60 plus I sine 4 times 60, which is 16 cosine 240 plus I sine 240. Well, cosine 240 and sine 240, that has a reference angle of 60 degrees, and we're in the 3rd quadrant, so both are negative. So 16 times the quantity negative 1/2 minus radical 3 over 2i. Distribute the 16, and you're left with negative 8 minus 8i root 3. So that's how you use de Moivre's theorem. Take the inside, convert it to polar form, and then use de Moivre's theorem and calculate the cosine and sine of those angles and redistribute the number outside. Example 2. Find the cube roots of 1 minus I in polar form. Alright, so we're going to use de Moivre's theorem to solve this. The first thing we want to do is convert 1 minus I to polar form. So let's find the absolute value, the r of this number. The r of this number is going to be radical 2 by adding the square root of 1 plus 1, because x is 1, y is negative 1. So if you factor out the radical 2 from the complex number, and then multiply each coefficient here by radical 2 on the top and the bottom, you're left with this number, radical 2 times times radical 2 over 2 minus radical 2 over 2i. Notice if you redistribute this, you're back to what you started with. So, in this case, cosine of theta is radical 2 over 2. The sine of theta is negative radical 2 over 2. We have a 4th quadrant angle. So, our reference angle is 45, which means our theta is 315. So, 1 minus I happens to equal radical 2 cosine 315 plus I sine 315. Now, what do we do here? Whatever each root is has to equal, well, each root that we cube has to equal this amount, because this is the number we started with. So whatever root is, we take to the 3rd power has to equal this number in green. So what we're going to do is we're going to call z a cube root of 1 minus I. In other words, z cubed has to get us this. De Moivre's theorem says that z cubed equals r cubed cosine 3 theta plus I sine 3 theta. So de Moivre's theorem, applying n equaling 3. Now remember, we know that z cubed, this root taken to the 3rd power, has to get us the number that we started with. So z cubed is equal to 1 minus I. But we also converted 1 minus I into polar form. And that is radical 2 cosine 315 plus I sine 315. So now we have z cubed represented using de Moivre's theorem in pink. We have z cubed in polar form in green. Now we just set those two values equal to each other and we solve for theta. So, and we can solve for r as well. R cubed cosine 3 theta plus I sine 3 theta is equal to radical 2 cosine 315 plus I sine 315. So now we're first going to solve for r. So we know that these two have to match. So r cubed equals radical 2. Radical 2 happens to equal 2 to the 1/2 power. If you take the cube root of both sides, you see that r is 2 to the 1/6, or the 6th root of 2. Now we have to solve for theta. Remember, when you solve for theta, any angle that's coterminal with 315 degrees will also work. So for any integer k, 3 theta has to equal 315 plus k times 360. What this k times 360 does, it'll get us all the values we need to satisfy 1 minus i's cube roots. So we know that if we divide everything by 3, we see that theta is 105 plus k times 120. So, between 0 and 360, we can plug in 0, 1, and 2 for k, and your thetas are 105, 225, and 345. So again, the reason we went to 315 plus k times 360 is because any angle coterminal with 315 would also be a solution. And we do this because we want to get all the values between 0 and 360. And if we only use 315 without the 360k, the only answer we get is 105, which is incorrect. So our answers are r cosine theta plus I sine theta. You just plug in the r for each one and the theta for each possible answer. So here are your three answers. 6 root of radical 2 times cosine 105 plus I sine 105, 6 root of 2 times cosine 225 plus I sine 225, and 6 root of 2 cosine 345 plus I sine 345. So again, the tricky part is to set the two equal to each other, and when you solve for theta, don't forget to include the k times 360. And notice again, there are three roots, which is what we should get, because I minus i's cube roots, there should be three of them. Example 3. Find the fourth roots of negative 16 in x plus yi form. So unlike in example 2 where we could leave our answers in polar form, now we have to take that additional step to convert all the numbers from polar form into x plus yi form by basically taking the sine and cosine of all the angles. So let's do this problem together, or if you want to try it yourself and come back and see if you did it correctly, you can do that. So first we need to convert negative 16 to polar form. In this case, z is pretty easy. It's 16, so r is 16. So we're going to factor out a negative 16 from our numbers, and if we do that, we get negative 16 equals 16 times the quantity, negative 1 plus 0i. So basically, we're converting this into polar form, or x plus y form, negative 16 plus 0i. So now, we're going to figure out that the cosine of theta is negative 1, sine of theta is 0. So if cosine theta is negative 1, our angle for theta has to be 180 degrees. So negative 16 is the same as 16 times cosine 180 plus I sine 180. Cosine 180 is negative 1, sine 180 is 0, so the I part drops out. Now, let's call z one of the fourth roots of negative 16, which means z to the fourth equals r to the fourth cosine 4 theta plus I sine 4 theta. We're using de Moivre's theorem and changing the n to a 4. So, if we're calling z to the fourth negative 16, that means z to the fourth also has to equal 16 cosine 180 plus I sine 180. So now we set the two equations to be equal to each other. And we first solve for r, and then we solve for theta. So, r to the fourth has to equal 16, so r is 2. Just take the positive number. The other numbers will take care of themselves. Now, we have to solve for theta. Now remember, 4 theta equals not just 180, but 4 theta equals 180 and all angles coterminal with 180. So 4 theta equals 180 plus k times 360. Now we divide everything by 4, and we get that theta equals 45 degrees plus k times 90 degrees. Now, if you plug in the values of k so that all your thetas are between 0 and 360, the four possible values for theta are 45, 135, 225, and 315. So, now we have to convert all of these into x plus yi form. So, our first root is 2 cosine 45 plus I sine 45. We also have 2 cosine 135 plus I sine 135, 2 cosine 225 plus I sine 225, and 2 cosine 315 plus I sine 315. Now we just have to find the cosine inside of all these angles, redistribute the r, and get our answer. This happens to be radical 2 plus I radical 2. Cosine 45 is root 2 over 2, so 2 times root 2 over 2 is radical 2. Sine 45 is root 2 over 2, 2 times root 2 over 2 is just radical 2. Here, you can get a negative radical 2 plus I radical 2. You can get a negative radical 2 minus I radical 2, and a radical 2 minus I radical 2. Notice that first quadrant, you're going to have both x and y positive. Second quadrant, you're going to have x negative, y positive. Third quadrant, both x and y are negative. Fourth quadrant, x is positive, but y is negative. And that's how you find the fourth roots in x plus yi form. First find the roots in polar form, calculate the sine and the cosines of all the angles, and write your answers. The final concept in this section is the nth roots of unity. The nth roots of the number 1 are called the nth roots of unity. Basically, it means z to the n power equals 1. And there are n nth roots of unity. And here's the formula. Now, basically what the nth roots of unity mean is that if you have, say, the 10th roots of unity, you're going to look for the 10 numbers where you take to the 10th power, they equal 1. And this formula is derived from de Moivre's theorem. If you want to figure it out yourself, you can. Basically, you're plugging in n instead of a fixed number. So cosine of k times 360 over n plus I sine k 360 over n. Each of these are one of the roots of 1, where k is all the integers from 0 up to n minus 1. So if you want to find the 10th roots of unity, you're going to have k with values of 0 all the way through 9, so you get 10 answers. If you wanted 20 roots of unity, you would plug in values of k from 0 to 19, so you get 20 different roots. Example 4. Find the cube roots of unity in polar form and an x plus yi form. So in other words, what 3 numbers cubed give you 1? So here is our formula for the nth roots of unity. Since we're solving for the cube roots, we're going to use n equals 3. So we're going to have 3 possible values here. Cosine of k times 360 over 3 plus I sine k 360 over 3, which means cosine of k times 120 plus I sine k times 120. Now we're going to plug in values of k all the way up from 0, 1, and 2. So let's start with cosine 0 plus I sine 0. Cosine 0 is 1. Sine 0 is 0, so the answer is 1, which makes sense because 1 cubed is 1. That's got to be one of the answers. Now we have the other 2 answers. We're going to plug in k as 1, so we have cosine 120 plus I sine 120. That's going to be equal to negative 1/2 plus radical 3 over 2. So hopefully you still remember all the Pythagorean trigonometric values because it's going to come in very handy here. Now the last root is cosine 240 plus I sine 240, and that's going to be negative 1/2 minus radical 3 over 2i. Note that this is a second quadrant angle. X is negative, y is positive. 240 is a third quadrant angle. Both x and y are negative. And these 3 values represent the roots of unity, the 3 roots of unity in polar form and in x plus yi form. The blue is in polar form. The yellow is in x plus yi form. So the roots of unity is a formula that you can use to calculate those values. That's the end of section 14.5. If you have any questions, you may ask me in person, through email, or post a message in the Facebook group.